Hey everyone, welcome to the second episode of the live white paper reading. If you haven't caught up on the first episode, so let me just give you a brief preview of what we did there. So, first and foremost, we talked about the different layers of the top ecosystem, how there is a infrastructure layer, there is an application layer, and there's a service layer. So, the application layer is the user facing model, right? So it is how we, one second please, it is how we interact with the rest uh, of the users, right? That's how they interact with the top blockchain through applications, and that is the application layer. Right below it is the service layer. So in the service layer, what happens is that we give different developer frameworks for our developers to build their applications. And since top is mostly in the communication region, in the communication area, that's where we base most of our developer frameworks on, right? Today, we are going to talk to you about the infra layer, the infrastructure layer. And this is pretty much the meat and potatoes, guys, right? Because for a proper infrastructure layer, for a proper blockchain project, the infrastructure layer needs to be as robust as possible. And we have once again touched on this in a bit in the previous episode. Because if you remember, we talked about the consensus algorithm, right? How top uses proof of stake and practical Byzantine, parallel Byzantine fault tolerance algorithm in conjunction to increase speed and security. But that is just the tip of the iceberg when it comes to the innovations in the infrastructure layer, so to speak, that we have incorporated in our technology. So, today, what we're going to do, today, we are going to talk about layer 0 architecture today, and then we are going to talk about layer 2 architecture. Layer 1 innovations or layer 1 architecture innovations, we will save for the third and probably the last video in the series. The reason being that layer 1 innovations that we have put in with multi-layer sharding and all those things, it's extremely innovative and in-depth and would require an entire video of its own, and we don't want to dilute the content that is going to be in this video. So without further ado, let's talk about layer 0 and layer 2. Layer 0, most of the blockchain projects that are out there don't really talk about layer 0 that much. The reason being that most of the attention is on layer 1 scalability, layer 2 scalability. But the problem with this approach is that they leave the layer 0 completely alone. Now, what is the issue with this? Layer 0 provides the entire base framework of your entire architecture. You can build the most majestic mansion or building in the world, but if it is on thin ice, then it's not really going to last now, is it? That is the problem that most of the major new projects, new and old both, face, is that they don't innovate the layer 0 area, right? And this is going to be an even bigger problem because now that many projects around the world are introducing sharding mechanisms like Ethereum 2.0 and all those things, that is going to be an even bigger problem then. Because if you don't have the layer 0 architecture that is fit to accommodate for all that innovative, amazing sharding ideologies that you're bringing in, then it's going to be a complete fail, isn't it? And so, how are we doing it? How are we changing our layer 0 protocols? How are we fine tuning our layer 0 protocols to make sure giving you the best service possible? Well, as you all may know, the base framework, network framework that all decentralized projects or all decentralized cryptocurrencies use is a peer-to-peer network. We don't use your typical client server model network because it's a centralized network. Peer-to-peer, on the other hand, shares the responsibility of the network upkeep upon all these different nodes who should have the same power in the ecosystem, so to speak. So that is the grinding protocol for a P2P network. And if you're aware about how torrents work, how BitTorrent and all these sites work, then that's pretty much the the OG peer-to-peer protocol, so to speak, right? And Bitcoin has built on it. And the way it works is that each node in this peer-to-peer system is supposed to download and maintain the blockchain at all times, and hence take part in the network consensus and network upkeep and all that amazing stuff, right? Unfortunately, the traditional peer-to-peer network, it has a huge downside in the sense that it is not as efficient as a centralized system. And it hurts me to say this, trust me. But as you know, centralized models, if you have the basic centralized model and you have a basic decentralized model, when it comes to speed and efficiency, the centralized model is always going to beat out the decentralized model, right? And that is true for your networks as well. And the as we said, along with sharding coming along, which requires a pretty intensive overhead among all the individual shards in the network to communicate with each other, is going to create a huge problem later on. Which is why at top we decided that before we even did anything, we needed to work on an optimized peer-to-peer protocol. And the way we did that is by creating a multi-layer P2P overlay, or as we like to call it, the peer-to-peer internet, because that sounds really fancy. So how does peer-to-peer network internet work, and what is the guiding design principles behind it? Think of what an internet is, right? Internet, in its very basic essence, is a network of networks. It brings together all these different networks under one shield and helps these networks to efficiently communicate with each other. What if we use that concept to create a P2P overlay that connects all these different P2P networks together? That is the guiding design principle that we are using here. And popular P2P network implementations have been optimized for certain use cases over the years, but they're not adequate for this ecosystem, because if you use a traditional P2P network for a modern architecture, you're going to be dealing with a lot of latency, right? Because, like we said, it's not as efficient as your traditional centralized networks. So the way we did that is by incorporating a lot of innovations that we are going to talk about right now, and these innovations are going to boost up our layer 0 capabilities, and at the same time create the ideal atmosphere or the ideal platform for cross-shard communications and for a sharding ecosystem. So let's look at how we do that. And so the first thing that we do is by using an innovative Cadmelia distributed hash table. If I'm not going to go deep into how Cadmelia works, but if you are familiar with these decentralized peer-to-peer protocols, then you know that Cadmelia's system is a huge part of this network, because that's pretty much how the nodes get mapped to each other, right? That's the core functionality of it. I'm really butchering it to make it as simple as possible, but that's pretty much, if you can think of it as a purveyor of a decentralized ecosystem, right? So that will give you a good idea. Now, the problem with traditional CAD layer system is that it uses a single CAD network for all communications between all the nodes in the system, in the entire network. And that is not going to be a very efficient system. So the way we innovate that is by using a multi-layered CAD network protocol, right? In our P2P internet, there will be all the P2P networks will be arranged in a hierarchical order, and each layer of P2P networks will have the information that is stored in the layer below it. And the way this is going to be organized is that we're going to use a zone, a cluster, and a shard. A shard, as you may know, is a collection of nodes in the normal network. We'll look into shards more in the next video. Zones are a collection of shards, and clusters are a collection of shards, and zones are a collection of clusters, right? And each zone in our network will be represented by one CAD network, and the clusters and the shards will be the nodes in this CAD network, right? That is, you can think of it like this: zone, cluster, shard, and multiple shard make up a cluster, multiple cluster make up a zone, right? And this zone, each zone is mapped to one unique CAD network. So that is the idea that we had, that if we are going to use a multi-layer P2P network, then might as well arrange them in a hierarchical way. So we are not clogging up the system, but at the same time, there's a connection, a real connection between the networks, so that there's no there's proper interoperability between the networks, because we don't want to create like a network silo, right? Because that is going to go against the very spirit of decentralization. And following our Cadmelia distributed hash table innovation, we have the XIP address. Now, you must know what an IP address is. Any asset that is connected to the internet has its own unique IP address. IP address is pretty much like the calling card or the location of that asset in that particular network, right? And the way it works is that if I want to interact with the system, and the way I do that is that through my computer, I send an information packet to that other node. That information packet is going to go to that IP address, and that's how we build our connections. Same idea we use for a P2P internet. In our P2P internet, instead of an IP address, we have a 128-bit construct that we call the XIP address. And the XIP address acts as the calling card for a particular node in our P2P network. So if we want to interact with other nodes, we have to interact with them through their XIP address, right? Now, up next, the next important innovation is zones and geographical clustering. Sounds complicated, but really isn't. So think of it like this. The way traditional CAD networks work is that in it, each node has its own unique node ID, which is determined through a XOR metric. So XOR, if you are not aware, is called exclusive OR. It's a binary operations operator, and it's a binary operations operator. I'm not going to go into a lot of details and show you how a truth table works, but think of it like this. It's a metric determined by binary operators that shows what the node ID of a particular node connected to the CAD network is going to be. Now, for efficient operations, what CAD does is that it clusters together nodes with similar node IDs into one cluster. And the way it determines which node IDs are going to be together, the way it determines how the node IDs are similar, is via the XOR metric with which it assigns the address, right? So, for example, node ID 1, node ID 2, node ID 3, just for an example, are going to be clustered together because they're similar node IDs. Now, this idea sounds good mathematically and theoretically, but when it comes to real life implementation, this method is not really the most ideal now, is it? For example, if I currently I'm in Asia, right? So if my node ID is 1 and somebody with node ID 2 is in Australia, that is not really the most ideal form of communication that we can come up with, right? So what Top does is that in the node ID of our CAD networks, we will introduce a geographical factor. So that way, nodes that are in Asia will be clustered together in one cluster instead of being clustered by their node IDs. Similarly, nodes in Australia will be in one cluster. Nodes in Europe is going to be in one cluster. One nodes in North America is going to be one cluster. 1 second, please. What this does is by reducing the geographical distance between the nodes, we are ensuring faster and more efficient communications. Remember, speed is the name of the game here. We can create a very fancy, poetic network, but if we don't have the practicality measures in it, then it's not really going to be an efficient system. And our idea is to create a network that can support real life implementations of different applications. And the way we do that is via geographical clustering, because if you have nodes in one geographical area in one cluster, they can easily communicate with themselves, right, instead of having them towards the in the opposite end of the world. So that is geographical clustering. And up next we have optimized gossip and data transfer protocol. If you are if you have studied networking in any time of your life, then you would know what the gossip protocol is. It is the core component of how nodes communicate inside a particular network. It is a core component of how Bitcoin works. It's a core component of how Ethereum works. That is a very important system. And to understand gossip protocol, remember back in high school when you had an embarrassing story about a friend, and the way you communicated it was like that you went and told one of your friends about it, and they then told their friend about it, and then they told their friend about it, and so on and so forth, until everybody got to know what that gossip was. Same system here. If I have node A with a particular, for example, let's think of Bitcoin's example, right? A miner mined a block, and miner itself is a node, and they want to tell the rest of the network that, hey, I mined a block. So the way they do that is that the miner is going to tell the other node about, hey, listen, I mined this block. This is the information that will show you that I mined the block. So give me the block reward. And that node checks and they're like, yeah, he's not wrong. He's right. He did calculate that. And then they pass on the information to the other nodes, and they keep on doing that until more than 2/3 of the network knows that, okay, this guy right here, he mined this block. He did it properly. So let's give him a reward. That is gossip protocol. And it is a very robust protocol. Don't get us wrong there. It is a very strong, secure, and very well-known and practiced protocol, right? But we feel that it's a little too robust. Uh, to I mean, it's a little too elaborate, so to speak. Like, for example, if I have $100, right, and I want to tell my friends, I want to prove to my friends that, listen, I have $100. I don't need to go and tell everybody, right? I can just tell 2 or 3 people, and this 2 or 3 people will be more than enough to validate the fact if I have that money or not. And that is what we mean when we say that the gossip protocol is a little too secure, because the amount of communications, the amount of network overhead that is required in passing just one piece of information, it's not really worth all that effort. So in order to optimize what we are offering, in order to optimize our layer 0 network, we needed to optimize gossip protocol. And the way we did that is actually pretty amazing. So like I said, the communication inside a network between different nodes happens by passing a data packet or an information packet, right? This data packet will be like, for example, if I want to say hi to node B, I'm going to send an information packet to their IP address, which says, hi, I'm saying hi to you. So that's how we're communicating with each other. But what we do is that we change this information data packet into a header and a body. A body takes up the majority of the size of the packet, and the header takes up is much smaller than the entire body. And like we said, that the different P2P networks in our protocol is arranged in a hierarchical order. So if we are sending somebody a data packet, the body of the data packet gets multicasted to the entire network, right? And then after that, if somebody wants to interact with somebody, instead of sending the entire data packet, we just send the header, right? We conduct gossip protocol just on the header of that data packet. So let me give you a better example of this. So for example, if I have, for example, I have a chocolate bar, right? and I break it into two, like one small piece and one large piece, and I tell everybody, look, this I have a chocolate bar right here, and that person is like, okay, tell me more about this thing. I want to know how it tastes like. Instead of giving them the entire bar, I'm just going to give a small portion of the chocolate to them, right? So that way they can just taste the chocolate and they will know what it tastes like. They don't need to eat the whole chocolate to know what it tastes like. And that is a pretty efficient method, so to speak, before communication overlay, because that way, instead of dealing with the entire package and dealing with having a gossip protocol put on your entire package, we can just do it with the slight portion of the package, and that way we can efficiently communicate. Now, moving on to the next part, the next communication protocol that we have innovated for our purposes, for our layer zero purposes, is called a reliable user datagram protocol, or a reliable UDP. Once again, if you're aware of how P2P networks work, then you will know that Cadmelia hash tables use the UDP for their underlying transport protocol. So as an underlying transport protocol, the UDP is usually fast, it has low overhead, it is ideal for a quick lookup and to see if the particular piece of information is correct and if somebody is mapped to a particular area properly or not, right? However, the problem with UDP is that it is not the most reliable of method because it is a connectionless protocol. And for most applications, if you use traditional UDP, then your network will not be able to give you the most ideal quality of service. All right. So that is the main problem that we have with UDP. And there are obviously different protocols. For example, Google's QUIC. It's a pretty reliable UDP protocol, and it can definitely work. But once again, the Quick protocol, Google's Quick protocol, it suffers from the same issue that gossip protocols suffer. They're good, they're secure, but they're way too elaborate. We don't need that much overhead. Our idea here is to optimize speed and security. If you can get the amount of speed, if you can get a reliable amount of security by just doing 50% of the process, then why do you need to do 100% of the process? Ironically, that is the core principle behind Google's SRE tech. It's the simple philosophy that has made them the proficient company in the world, right? So that is the core idea there. That instead of having a way to extra elaborate method, just do an optimal method that is enough to conduct the operations in a fast and secure manner. So the way we do that is that we have created our own UDP protocol called XUDP, and the protocol is customized to only include the necessities and maintain low overhead, high speed, and optimal security. All right, so we have now moved on to the last innovation that we are doing in the layer zero level, and that is called smart routing. Now, routing is a term in networks that is used to define the path that a data packet takes to go from point A to point B. Traditional Cadmelia DHT is completely end-to-end, and there is no optimal paths for the data packet to follow. So, for example, like the age-old question, right? Do you touch your nose like this, or do you touch it like this, right? So that is the main issue that we're going to solve here. And the way we solve our this routing issue in our protocol is with a smart routing system. So when connecting to another node, the lookup process will eventually provide the details required to make a direct connections. In our system, in our layer zero protocol, we test out several different paths between node A and node B. We're going to test it out continuously, and then we choose the most optimal path, and we take that path for a data packet to follow. Because so that way we minimize the time taken and the network overhead required for transformation protocols, and that is the final innovation that we have in a layer zero system. So up next, what we are going to look at is a lattice structure, and that is another very interesting system we're going to use here, because with our top chain, we have the combination of a public blockchain along with a directed acyclic graph, or a DAG, that has been made famous by projects like IOTA. So what do we do here, and how do we incorporate a lattice structures to increase the speed, scalability, and security of a system? So in our top blockchain state, which is made up of all the user account objects and the smart contract account objects, it is stored in two different data structures. We have the unit lattice structure and we have the block lattice structure, right? So let's look into unit lattice structure. Every transaction record made by any account in top is called a unit. These units are linked together to form like a unit chain, and each account has a unit chain of its own. So what does this mean? Every account in top will have a mini chain in itself. It's not a blockchain, it's a unit chain. Every transaction that you have made, every transaction record, think of it as a transaction chain that is stored inside each unit, right? And the set of all the account chains in a shard forms the unit lattice structure. So as you know that each node is placed in one shard. So for example, if I am in shard 1, I'm an account that's in shard 1, I cannot be present in shard 2 and 3. It's a one-to-one relationship. So each and every shard will have its own unit cluster of unit chains for all the nodes and accounts that is being stored inside it currently. And these chains itself form a unit lattice. So what is the main purpose of doing this? If you do a unit lattice structure inside a shard, then you can add another layer of parallelization during the consensus process itself. So not only is a consensus happening in the block level, but the consensus in parallel can happen in the account level itself. So if you go with a traditional structure, this one main consensus layer will be conducting the block consensus and the unit transaction consensus. Every single thing it has to do by itself, and it unfortunately needs to happen in a sequential order, which is not really that effective in this day and age. So what we're going to do is that we're going to have the main chain consensus. At the same time, we will have the unit account consensus, and these two will work with each other in parallel, right? So that is the unit lattice structure. Now let's move on to the block lattice structure. So remember how we just literally talked about the unit chain, the transaction chain that is going to be stored in each and every account. So for each account or unit chain, the last unit of that chain includes all the important information of that particular account, like the current balance and any other interesting metadata, right? So what the block lattice does is that it takes up this last unit things and it just clusters them together and packages them into blocks. And these blocks form a block lattice, and they are linked into the chains of each account. So what is happening here is that each account has its own unit chain, own transaction chain, which is clustered together in each shard to form a lattice. The last unit block of each of these accounts are stored in a block lattice. So if you can think of it like, for example, if each and every accounts, their important details that I can pinpoint them to different layers of communications is stored in the block lattice. So why do we do that? If in cross shard transactions, right, in cross shard communication, if shard A wants to communicate with shard B, the way they do that is via the receipt transaction that is stored in the block lattice. That is the main idea here. And if we don't have a block lattice separately for this, then cross-shard communication is going to be extremely complicated. So that is the reason why we have a unit lattice and a block lattice structure, two-layer lattice structure, which is further incorporated onto the blockchain. Now, why do we even have a DApp structure in the first place? We have a blockchain, right? We have shards. Why do we need DAG structures on top of that. And how different is it than the existing DAG models that have been made popular by IOTA? So why do we have that is, as I explained, for efficient communications and efficient security and all that other lovely stuff. And the way it is different from IOTA and all that thing is that our lattice structure, two-layer lattice structure, is a lot more organized and more optimal for sharding purposes, like we just explained with block lattice. Traditional DAG is not that good for sharding. This our two-layer lattice system has been made for sharding, so to speak. All right, so we just crossed layer 0, so good for you. And we are not going to talk about layer 1 right now, because like I said, it's a very intense topic that requires a video on its own. So we are going to jump onto layer 2, right? So what is layer 2? And if you are aware of what Lightning Network is for Bitcoin, Raiden for Ethereum, ZK rollups for Ethereum, and Plasma for Ethereum and Omisego, then you will be very well aware of what layer 2 is. So think of it like this. Layer 2 is an extra architectural formation that's built on top of the main blockchain, wherein the blockchain can delegate complicated processes and complicated calculations to the layer 2 structure to reduce the main blockchain's bloat and to increase overall speed and scalability, right? So for a very generic understanding of how layer 2 works, let's look at how Lightning Network works in Bitcoin, right? So in Bitcoin, if I want to send one Bitcoin to my friend, and I don't have one Bitcoin, if you have, then please send it to me. Not really. So if you have a friend and you want to send one Bitcoin over to them, the way you do that is that you create a transaction. In this transaction, you put in the motive of your transaction, that hey, I want to conduct a transaction with my friend Bob, and here is my one BTC. Please send it over to them, and we're going to sign it off with a digital signature. After that, we put the transaction in the Bitcoin network, and the transaction goes to a place called the mempool, which is like a queue of transactions, so to speak. Now, a miner picks up these transactions from the mempool, validates the signature to check if it is coming from the right person or not, and then they put it inside the block. And then when the block gets mined and added to the blockchain, that is when the transaction finally goes through. And a block time in Bitcoin is around 10 minutes. So you are looking at somewhere around 10 minutes to 20 minutes for a transaction to go through. Not good, right? Now, what layer 2 suggests is that one more thing. So if you and your friend are the kind of people who always transact with each other through Bitcoin, and you're not really sending one BTC, right? You're sending 0.001 BTC or some microtransaction like that. For this purpose, the traditional structure of Bitcoin is not really well suited for you, because you have to send a transaction fee for each and every microtransaction. It can get very expensive for you. So the solution here is that you use a layer 2 mechanism, which is, think of it like a detour from the main blockchain, which connects you to your friend directly via multi-signatures. In this layer 2 zone, you and your friend can communicate with each other as many times as you want. If you want to send 100 transactions, go ahead, be my guest. Following that, after we conduct a lot of transactions, we commit the final state of the transaction to the blockchain. So, for example, suppose that in the beginning of the layer 2, I had one Bitcoin, my friend has 0 Bitcoin, right? I send over 0.2 Bitcoin, now I have 0.8, he has 0.2. We keep on transacting, and at the end of the day, I end up with 0.6 Bitcoin and my friend ends up with 0.4 Bitcoin, right? So instead of conducting all these transactions through the blockchain, we just commit the final state of a microtransaction wherein I have 0.6 Bitcoin My friend does 0.4 Bitcoin. We just commit that to the blockchain. It is a really, really, really efficient process. It's a really, it reduces overhead by a huge amount. It reduces the overall transaction fees that you will need to pay eventually. And overall, it's an amazing innovation. And same goes for Raiden as well, right? So that is the core concept of how layer 2 works. Now, we also want to integrate layer 2 in our protocol, and the way we do that is via one-way state channels, which are also known as service chains, right? So why are we doing something new altogether again instead of going with the existing protocol or the existing design formulas that we are aware of, like your Red and Lightning Network, etc.? Is because these existing implementations have three big problems. First and foremost, it assumes a generalization of interactions. Majority of the layer 2 solutions out there are working on a philosophy that one size fits all. While it may seem simplistic and it may seem ideal to go with that state of mind, the reality is that this approach is extremely challenging. Different operations will require different implementations, right? A transaction is extremely different from a smart contract interaction. So you cannot have a one size fits all philosophy there. Secondly, is the architecture problem, and this is especially pertinent to Ethereum and Bitcoin. Bitcoin and Ethereum already have a very well established blockchain, right? They have been around for years. They have thousands of nodes, and they have already have a lot of network interactions within the entire system itself. Now, introducing a layer 2 architecture on top of this blockchain that has already been established can create a huge unnecessary headache, because can you imagine what can happen if they mess up the implementation? They can disrupt their entire system, and a worst case scenario, there will be like a bug in the entire network which can be exploited by a hacker, and God knows have we not had enough of those in the past. And second thing is that if not like a bug itself, it will definitely require the system to go through many hard forks for it to be properly implemented. And again, Bitcoin and Ethereum have a very bad history with hard forks, right? So now the third thing is the two-way verification system. In a standard state channel like your Lightning Network or your Raiden, the settlement and dispute process of these transactions can be very complicated. All the participants in the channel must completely agree on every single state transition. If one of the participants goes offline, or maybe if there's some sort of like disagreement, or somebody agrees, or somebody decides that, you know what, I'm just going to like mess up this entire system here, then the entire settlement and process and the dispute process becomes a huge headache that you do not want to deal with. The process can take a long time, which completely negates the point of having a state channel in the first place. So what is Top Network's solution here? To understand this solution, you have to first understand the concept of service chains, right? Service chains in Top are pluggable state channels, side channels that are built on Top's blockchain. And it caters to a specific use case. So for example, we have a service chain for like microtransactions. We have a service chain for like games, stuff like that. If you have a unique use case, then you will have a service channel that's already built in to the Top's blockchain. So these state channels are built in, these service channels are built in, and can only be used for applications that conduct low value, high frequency microtransactions, like we explained in the examples above. Because the only reason why you need a layer 2 architecture is to conduct these fast microtransactions, so that you don't have to go through the entire headache of going through the main protocol itself, right? It can be extremely cumbersome and time consuming. The state channels slightly differ from each other based on their specific use case, right? So an example that is specific to Top is our VPN service chain. The main participants in your typical VPN service chain transactions are a VPN client, a VPN service provider, and the VPN edge node relays. Now, the way all these things come together with a service chain is that, think of this scenario. A VPN session is built based on billing units. A billing unit is around 1 MB of bandwidth, which is exceedingly small amount. As such, it could take thousands of these transactions to finish just one session. So instead of having to go through the main blockchain itself, we have the VPN service chain, which can be connected to a particular transaction through a virtual smart contract, right? And the idea here is that through this service chain, VPN service chain, the VPN service provider and the VPN client can conduct like thousands of transactions between them and finally commit the last state of the transaction to the main top blockchain. So what are the advantages of this? First and foremost, it is a use case specific solution. It's not a generalized solution. We do not have a one size fits all policy. We have a size that is the best suited for your policy, if that makes sense. Secondly, is the architecture issue. We are not adding any unnecessary overhead or any unnecessary architecture to an already existing blockchain. Our service chains are already plugged in. Our use case service chains are already plugged into the main blockchain. And thirdly, we don't have a two-way state channel. We have a one-way state channel, which makes sure that participants don't waste their time in settlement and dispute. Unlike the Lightning Network, where both the client and service provider will need to agree on the current state of interaction, in top, the client has the final say. So if a discrepancy does occur, the state channel is completely shut down and the client pays the last amount that was logged in the virtual smart contract that is overseeing all the interactions that are happening in this service chain. So yeah, that is the main idea of a top state channel. So if we were to compare the three big layer 2 protocols like your Lightning Network, Plasma, and top state channels, then the framework for Lightning and Plasma is not built in. For top state channels, it's already built into the main blockchain. And Lightning Network can be used for payment only. Plasma is basically a nested blockchain architecture to solve different operations in parallel. Top state channels, on the other hand, they're use case specific state channels that are built for efficient scalability. So that is the core design principle behind our our one-way state channel, so to speak, or also known as the service chain. So yeah, this has been a pretty big video, hasn't it? 42 minutes and counting. So like I said, layer 1 scalability like sharding will require its own videos. So keep an eye out, and we're gonna release it soon, and much sooner than this was released. And if I am also going to conduct a lot of create a lot of top class videos. So if you haven't checked them out, then do check them out because they are extremely useful and it will help you understand the different blockchain concepts used in top in relation to the concepts that are in general out there, right? So I hope you gained a lot of insight from this video. I do recommend that after watching this video, you do read the particular sections in the white paper that I talk about here. And yeah, that's pretty much it. So I hope you had a lovely time. I certainly did. Bye.